So this is the basics of ordinary differential equations here in a numerical analysis class. Most, if not all of you, have learned some differential equations in the past, but even if you haven't, I do want to help you enough that you can do what you need to do for this class. We are talking ordinary differential equations as opposed to partial differential equations. Ordinary differential equations involve ordinary derivatives, one variable calculus derivatives, you might say. Partial differential equations involve partial derivatives, multivariable calculus. And as you might expect, partial differential equations are harder than ordinary differential equations. You need to understand ordinary differential equations before you can understand partial differential equations. And we are mostly going to focus on what are called first order ordinary differential equations, ODEs. ODE stands for ordinary differential equations. PDE stands for partial differential equations. We also just sometimes say diffie-Q for short, or diffie-Qs for short. I'm not sure of all of Dr. Auk's quirks with differential equations. I spell diffie-Q different than he does. I tend to spell it with 2 Fs. I think I've seen him spell it with 1 F. Sometimes I make the Q capitalized just because I like it. And sometimes if I'm feeling extra wacky, I do it this way. Diffie-Q. Okay. Another quirk is that depending on the differential equations book you use, the derivative you write here might be written dy dx, or it might be written y prime, or it might be written dy dt. I like writing dy dt. I don't know what textbook you used like writing. The way I like writing it that way because almost all the applications I like to think about, at least, the independent variable is time, not position or something. So I like dy dt, and that's what our book uses, though they often do write a y prime for short. It's first order because this differential equation is only going to involve a first derivative, not a second derivative. Such an equation would be a second order equation. We will talk about second orders a little bit, but mostly we'll focus on first orders. And in simplest form, I mean, the differential equation doesn't have to be solved for dy dt, but it's sort of simplest if you imagine it is solved for dy dt. The right-hand side is some function of both t and y in the general form here. This is a general form. And the question is, what is that function f that's on the right-hand side of the differential equation? Different right-hand sides produce different equations, produce different solution methods. Some easier than others, some harder than others. Some equations are pretty much impossible to solve. In fact, you might even argue most equations are impossible to solve. So what's the point? Well, just because they're impossible to solve symbolically through various methods doesn't mean they aren't important and valid equations whose solutions do exist and can be approximated. It's kind of similar to how some integrals can be done quickly and easily by hand. Some are a bit harder because you got to use partial fractions or something, or some substitution. And some are, quote unquote, impossible to solve exactly with elementary functions. You got to use non-elementary functions like the ERF function or the gamma function or something like that, with some kind of crazy integrals that you've encountered in more advanced math. It's a similar kind of thing that's going on here with differential equations. The simplest kinds of differential equations are where the right-hand side, this f function, only depends on t, the independent variable for the unknown function we're trying to solve for. The simplest kind I call pure antiderivative problems. they're nothing more than just a plain old calculus problem. dy dt equals f of t. The general solution for y as a function of t is just found by integration. Done. I'm about to do something that I do when I teach differential equations with linear algebra. I don't know if Dr. Auk does this in plain old differential equations. I like giving the solution function another name. I will tell you our textbook abuses notation and calls it y of t, but this is abuse of notation, not abusive notation, but abuse of notation. To use the same letter y for both a variable name and a function name is technically bad, but you see it done in both math and science textbooks, and people just live with it. I like emphasizing that it's bad and using another letter, and what I like using is the Greek letter phi, or phi if you prefer. Phi of t as my symbol for the solution function, and that's better notation. Okay, Dr. Auk use a phi or not? No, no, okay. I like doing it for a number of reasons. First reason is because, hey, it is better notation to give a different function name than the variable name. And secondly, because I just like Greek letters. And thirdly, because you will find it in other differential equations books. Some of them use this notation, and they do seem to traditionally use the Greek letter phi, or again, phi, if you prefer. And fourthly, because it's also related to a subject near and dear to my heart, related to my thesis work, my PhD thesis, on the subject of what's called a flow of a differential equation, where it is very traditional to use this letter. And there are lots of good reasons for it, and I'm not going to go into those right now. Anyway, it's just the general antiderivative of, little f of t dt, which will be something plus c, where c is an arbitrary integration constant. I'll just write antiderivative there. You know, in calculus, you typically call the antiderivative capital F, and we could do that here, and that would be fine. I'm just saying I'm not doing that. Antiderivative of little f. We want the most general antiderivative. We add an integration constant. Though, if we take this differential equation and add an initial condition, then we can solve for c. This by itself is just a plain old differential equation. Its general solution is really a family of functions. There's infinitely many possibilities, because c can be anything. But if we add an initial condition, and here I do not buck tradition, and I do use a y with abusive notation. Y of t0 equals y0, or as our book does, or here's how our book writes it, y of a equals alpha. That's the way they do it in our text. Based on that, we can solve for c. And you've done that in calculus. And you get one value of c and one function that solves both the differential equation and satisfies the initial condition. We get a unique solution to what's called an initial value problem. Talking generalities here today, but I think this is still good. With these generalities, I'm not going to assign any homework except reading, and the reading's harder, but do it anyway. Next Tuesday, we'll look at specific examples and solution methods like separation of variables, integrating factors and that kind of thing, which you've probably done in the past. and some applications. The next simplest, or maybe I should say next hardest, or maybe just harder. Let's say it that way. Harder is called an autonomous differential equation. It's harder, but it's not the hardest. Autonomous ODE, where dy dt equals f of y. And again, you can write y prime if you like as well, but it's understood I'm going to treat t as the independent variable here. That's a harder kind of equation. You cannot solve this by integrating f. Because if you do, you're misunderstanding what this equation is saying. So what is it saying? Maybe we should do one example. Here is a simple example of this harder situation. Simple example of harder case. Dy dt equals y. What is the solution to this? I hope it was clear from your past or from what I was talking about here that solutions are functions. They're not numbers. Same here, solution's a function, not a number. And the answer here, do not be tempted to say the answer is 1/2 y squared plus c. Completely wrong. We're not going to integrate with respect to y on the right-hand side. You have to understand what this differential equation is saying. Pretend it's talking to you. Hey, you, I'm after a function whose derivative with respect to t is always itself. A function of t whose derivative with respect to t is always the function itself. A phi of t such that phi prime of t always equals phi of t. Hey, we know such functions. E to the t, 2e to the t, 3e to the t, -17e to the t, or any constant c times e to the t. The general solution using phi notation is y equals phi of t equals any constant c times e to the t. The answer again is not 1/2 y squared plus c. I'm not after a function of y, I'm after a function of t. In the model, t is the independent variable off in time. Y is the dependent variable. Y depends on t. We're after a function of t whose derivative is always the function of itself. Y is the function itself. This probably would be a better way to write the differential equation. I'm after an unknown function phi of t whose derivative is always itself for all t. It's just not traditional. It's traditional to write it that way. This is the hardest thing to get across in the first week of differential equations to students. You're after a function of t whose derivative is always itself. Yes, functions like that, where c can be anything. And once again, you could have an initial value problem. And by the way, when you write initial value problems, IVPs, you typically write it as a system of equations. dy dt equals y in this case, say y of 0 equals y sub 0. The unique solution of that initial value problem would be phi of t equals y sub 0 times e to the t. Because if you plug in t equals 0 here, e to the 0 is 1, y0 times 1 is y0. Here I'm thinking of c as arbitrary, so it can be anything. So this represents infinitely many solutions. Here I'm thinking of y0 as fixed or given. So I'm thinking of this as just one function. But of course, y0 could be anything, so it could represent infinitely many answers. It's all in how you think about it, whether something's a constant or arbitrary. Okay. So yes, this is a general introduction to differential equations. The hardest case, so this is the simplest. That's the harder case. The very hardest case is when your right-hand side depends on both t and y. Yeah. Though even within that, there are special cases where it's easier, where the equation is separable and you can separate variables, for example, if you remember that. And after you separate variables, then you can do integration to solve, but you got to be careful because it's tricky.